Hello, if you follow the channel, you probably endured a short format YouTube video filmed the wrong way, so you know that I recently visited my friend Jack Rubin in Michigan, and that we booted his HP 1000 to test the paper tape drive. It's a step I highly recommend you do when you receive your new HP computer. Now that I have returned, here is the fuller story of the visit, filmed in the right orientation. Hi, this is Jack.
Hello.
This is Jack's den. What do you call this place, Jack?
This is the Computerarium.
Yes, it's the Computerarium, a place for old and strange species of endangered computers to swim freely without fear of being eaten by new, faster computers. Like me, Jack has a particular liking for vintage HP instruments and computers, and has been collecting a lot longer than me. I could recognize quite a few HP instruments swimming around.
It's an HP 200BR audio oscillator.
Whoa, an HP 200! It's HP's first product, here with young Bill Hewlett and Dave Packard in their famous Palo Alto garage.
HP 5512A electronic counter. HP 9865A cassette. Teletype Model 15. PDP 8E. HP 9825.
And he has almost as many as I have. Oops. Except this one's a printer on top. I don't have that.
HP 9830.
What? You have an HP 9100? Wow.
The memory and the plotter.
The whole shebang. It works?
Yeah.
Does it work?
9100 works.
Okay.
Yes.
Oh, maybe we'll try it. This is the first time I saw a 9100 working. HP's first programmable scientific calculator. Pretty. 2 square root. Enter to move it to the Y register. Multiply the 2 to get the square. And we're back to 2 exactly. All the scientific functions you ever dreamed of, and you can even program it. What's that big beast?
This is a HP 2109 or an HP 1000E. Ready to work.
And
7900 disk drive. 2748B paper tape. 2116C, which is really the star.
yeah, that's the predecessor to that one. Right? So
Right.
this came, and then that's the grandson of that one.
Yeah. Well, twice removed. And then 7970E tape drive.
So the HP 2116 was HP's first computer, introduced in 1966. That's the machine that started HP on its current computer path. It was a specialized computer for real-time test and measurement automation, fitting perfectly into HP's core business. Then it got shrinkified into the HP 2100 in 1971, still using core memory. Then it got upgraded to semiconductor memory, one of the very first machines to do so, and became the 21MX in 1974. But after a period of major naming confusion, the 21MX eventually got rebranded the HP 1000M. It progressively got more powerful successors, the 1000E from 1976 and the 1000F from 1978, which look almost exactly the same. The different sizes mainly relate to how many more empty slots you have to add memory and interface cards expansions. Jack's computer is the middle of the range 1000E. And we forgot, we also have the little green terminal on the side. What are we going to do with it?
And if we are lucky, we're going to use the processor to run the tape drive to load the diagnostic program to test the paper tape reader.
So today is going to be a light episode. We are just going to boot the machine, get it to load the master test program for the magnetic tape drive, and use that to run the paper tape diagnostic test. You'd think it would be a piece of cake, but it isn't. Starting these machines is notoriously difficult. On the early machines like the 2116, you had to paddle in the first 64 words of boot code with the front switches in glorious 16-bit binary. Thankfully, they were using core memory, so your hard work stayed there even when power was off. The later 1000E has regular silicon memory, but thankfully it has the startup code in small resident ROMs. Or should we say startup codes, as there are 4 different ROMs with 4 different boot codes that you can start from. Each is used to boot from a different type of peripheral, such as a disk, a magnetic tape, or a paper tape. But you still have to construct and paddle in a 16-bit word that will tell the computer which of the 4 ROMs to start from, and which is the slot number for the card that your corresponding peripheral is connected to. That's what Jack is currently trying to do, so far not so successfully, using the magnetic tape as our boot device.
Yeah. 100. Store.
You're on P, yeah, that's correct.
S.
Yep.
1, 6. Store. Run. No.
Doesn't like it.
Store.
Okay, I think we got it. We finally paddled in the correct start word. To make it more fun, this uses octal grouping, not hexadecimal. So you can see the 16 register bits divided in groups of 3, which gives you 5 digits and the first bit of a 6th one. Starting from the left of the register, we have 0, 4. That means that we are using ROM number 4 to start, the one used when booting from a MagTape device. Then the 2 next digits are 1, 3 in octal binary. That means that our tape controller card is in slot 13. We store that in register S as indicated by the row of 6 LEDs below the main row. We reset the machine, initial boot load, and press run. That should launch the ROM for boot code, which will start the tape and read the rest of the boot program from tape into memory.
Okay, now we should see a tape load. Okay.
Okay.
Store. Here's IBL run. Queued up.
Bingo. But when it's done, it does not continue to boot. No, no, no. No newfangled user-friendliness varnish that gets in the way and hides the important inner workings that we deserve to know. Instead, it stops, or more exactly, the processor halts. Then it displays a halt code that indicates if the initial load was successful or not. The code here is 102077, which obviously means success, as is customary for HP 1000 halts. Yes, I know, don't ask me why.
So P 100 store.
So Jack just entered 100 in register P. This is to tell the computer where to continue to boot from. We store that memory address 100, which points to the code we just loaded from tape, in register P, the program counter.
So S16 store.
We also have to tell the boot program where our terminal is connected, so it can display the results on our screen. In our case, the terminal interface card is in slot 16. Jack entered that into register S.
Run. Something happened over there.
Yep. That did work. And for a moment I was expecting the tape to run again, but of course it did not, because we were simply running the boot program that we already loaded in memory. However, our terminal at address 16 woke up. Woohoo! Amazing! We have a user interface. 21MX line printer. It wants to know what your line printer is.
Okay. N-O-N-E. Didn't like that. N-O-E. So I got a space in there, yeah. Input device is 7970. Select code is 13.
7970 stands for HP 7970, the model of our tape drive. It is still connected to the same interface on slot 13. But of course we are now running a different program, so it does not know what we told the ROM bootloader a second ago. We have to tell it all over again. And that's our tape drive.
Yep. Okay. DSN is 146200.
Finally! That's the number of our paper tape test program. There are many test programs on this reel, one for every existing piece of hardware that connects to the HP 1000, plus internal tests for the CPU. Here we use the Mac tape to load the test for the paper tape, but the inverse is also possible.
Now it's going to spin like crazy. Backed up all the way to the beginning of tape.
Probably because so it can count.
Should know where it is.
Now the computer is automatically searching for the appropriate test to load from the tape, and it's quite a ways off. Here is a halt again, and since you are in the know already, you recognize the 102077 code, which means all is good.
I'm going to set this register to 17 for the paper tape reader.
This is similar to what we did with the boot ROM. We have to tell the test program on which slot our paper tape hardware controller resides, also known as its select code. In our case, the tape controller is in slot 17. Note that you don't want to do the newbie mistake and load it in the two last digits, but like a seasoned professional, you put it correctly in digits 3 and 4 right in the middle. Congratulations!
Then we're going to set P, program counter to 100, store that.
Once again, we set the program counter to 100, the memory address at which the program starts. Very good, you are starting to get the hang of it.
Reset, run, alt, 74, success.
Okay, we ran it and it halted with a 102074 this time, which is success for this program actually. Just a little change to keep us on our toes.
Yes, register to 9. which means that I'm going to manually select the test, store that, reset, run. So now it's going to ask me to choose a test.
Yep.
The A register for the test that I want to run, which is test 4. Store that. Set S back to 0. Store. Reset. Run. Okay. We got a halt 54, which is correct.
So set bit 0 to 1.
Now I'm going to set S register bit 0 to 1.
Okay, take a step to the left so I can see the...
And we're going to run that sucker.
Okay.
I'm going to set S 0 to 1.
It's running!
And we'll set it to 0 will stop. And if I set it to run, to 1, to 2, maybe run next. Let's do this. Set it to 1. Store it. That's all.
It doesn't... That's it for today!
That's it, folks. That's all, folks.
Alright, that felt like an achievement. It's very much like we still do today, when we finally get a command right on Linux. Very rewarding. Thanks, Jack.